Rows and columns show up everywhere in linear algebra. Take matrix multiplication. All you're doing is taking a row of the first matrix, a column of the second, and taking the dot product. How about matrix vector multiplication? Well, that's just a linear combination of the columns of the matrix. So naturally, you'd expect there to be some notation for rows and columns, something like this. Except, no, there's no notation. This doesn't exist. And that's strange because the moment you have this notation, a lot of important formulas suddenly become obvious. This notation doesn't exist, so today we'll invent it. Okay, let's start with the column function. So col sub j is the function which takes in an m by n matrix and outputs the jth column of that matrix. For example, col sub 2 of this thing would return the vector -1, 2, 5. And for rows, the ith row function will take in an m by n matrix and output the ith row of that matrix. But there's a slight caveat here. For example, the second row of this matrix is the 1 by 2 matrix, which is 4, 2. It's not going to be the column vector 4, 2. So that's how we're going to define it, and that just makes some formulas nicer. So this way, the column function returns a column vector. That's basically what you call a normal vector. And the row function returns a row vector, which is a 1 by something matrix. Now, can we find a formula for these in terms of A, I, and J? We'll also do it for the ijth entry, not just the columns and rows. So let's try this. First, let's do the column. Okay, so we're going to assume that this has a nice form. We'll assume the formula is a matrix product, meaning we'll assume that there's some special matrix C such that A times C would extract the jth column of A. And we just want to find what that matrix C is. Now, if we do that, first of all, we should think about sizes. If A is m by n, then C has to be n by something for these to be able to match, right? Because we're multiplying them. The result is going to be m by p. But we want the result to be the jth column of A, which is a vector. So it should have only one column, meaning we need p to be equal to 1. So that means C is going to be n by 1. In other words, C is a vector in Rn. So this is a bit misleading. Let's just call it V instead. So it's just clearer that this is going to be a vector. So we're going to look for this special vector V such that multiplying A by V will extract the jth column of A for all matrices A. Now, because this works for all matrices, we can actually be a bit clever and choose a specific matrix which simplifies things. Usually we would do the identity matrix, and you can see why, because this gives V equals the jth column of the identity. So there we go. The special matrix V is actually going to be a column of the identity matrix. An arbitrary identity matrix looks something like this. The jth column would have a 1 in the jth position and 0 everywhere else. And we actually have a name for this vector. It's called EJ. EJ is the vector with 1 in the jth position and 0 everywhere else. And this is the special vector such that A times that vector will give us the jth column of A. And this works for any A, as long as you choose the right sized EJ so that the matrix multiplication works. And you can check for yourself that this really does work. AEJ does return the jth column because AEJ is a linear combination of the columns of A. And because everything here is 0 except the jth position, only the jth column remains in the sum. And we do indeed get the jth column of A. If you didn't know this thing about linear combination of columns, check out one of my previous videos. I'll link it in the description. Okay, so the jth column of A is AEJ, but how about rows? Well, we don't actually have to do much else. We can just use the transpose, because the transpose acts as a bridge between rows and columns. The ith row of A is actually the ith column of A transpose. Well, kind of. The ith row of A returns, well, a row vector, while the column returns a column vector. So technically, these aren't true. We would need to put A transpose again here and transpose the column vector. Then this is indeed an equality. Well, we already know what the ith column of A transpose is. It's going to be A transpose EI, right? Now, just to clarify something, A transpose is n by m, because A is m by n, and that means EI has to be m by 1 in order for this matrix multiplication to work. So EI is going to be in Rm. And then now when we take the transpose, we can use the transpose product rule, and we get EI transpose A transpose transpose, or EI transpose A, which is the same thing. So that's the formula for the ith row of A. You just left multiply by EI transpose. How about entries? Well, what does the ijth entry of A mean? Well, it's the entry in the ith row and jth column, right? So you can actually use that idea and use both the column and row formulas to find a formula for Aij. You can try it yourself, but we're just going to go through it as well. So we're going to use this pretty nice idea. The ijth entry of A is the ith row of the jth column of A. So what does that mean? Well, first let's just do that. Ith row of the jth column. And using the formulas, you get EI transpose AEJ. It has a nice ring to it. But if you want to see an example of how this works, take this matrix here, and we're after the entry in the third row and second column. That would be the entry 8, right? So if you do the row column thing here, you get the third row of the second column, which is the third row of the vector 3, 5, 8. But the third row of that vector is, well, 8, right? So you can see it does work. Now what's a bit weird here is technically this would be the 1 by 1 matrix containing 8. Not really the number 8. But in linear algebra, we often treat 1 by 1 matrices as scalars, as numbers basically. So this should be fine. So these are our three formulas: AEJ, EI transpose A, EI transpose AEJ. We also have some nice results regarding matrix multiplication. The ith row of AB is the ith row of A times B. The jth column of AB is A times the jth column of B. This means if you want to find the columns of AB, all you do is you take A times the corresponding column of B, and then that's how you get it. Also, the ijth entry of AB is the ith row of A times the jth column of B. This is basically a row vector times column vector sort of thing, and I showed something like this in my previous video if you want to understand that better. So have a go at proving these if you haven't already. There's also something about linearity. It tells you that the ith row of a sum is the sum of the ith rows, and the ith row of the scalar multiple of a matrix is that scalar multiple of the row. Similarly for columns. These are pretty intuitive, I guess. Then of course we have the transpose one. We already discussed this in the video. Now I'll leave you guys with a practice question. Prove that an n by n matrix A is symmetric if and only if it has this property with dot products: x.ay equals y.ax for all vectors x and y in Rn. By the way, a symmetric matrix is just one which is equal to its own transpose. So that just means A equals A transpose. So yeah, thanks for watching.